All right, absolute value functions. This is what we're doing for this lesson. And so first, this is taken from the notes. You see, we can use the piecewise function of these two different rays and the line at zero to create what we call a V-shaped graph. Now, the corner point there, we call that the vertex. That's important. We're going to come back to that not only with absolute value functions, but also with quadratics. All right, so if we were to take this and graph this, we would actually get this function. And so instead of splitting them up, what we're going to learn is just how we can put them all together to get our absolute value function. And what you see here is that if I was just to graph the positive xi when x is greater than 0, I'll get this portion. Since it's just strictly greater than, we can include the x equals 0 just so that we have a point at 0, and then graph the negative x when x is less than 0. Now, just in case you don't recall this, to draw the line y equals x, you're just simply putting a point through every duplicate of x and y. So 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. The same thing with negative x. It's just going to be the x is negative. So you can have negative 1, 1, negative 2, 2, negative 3, 3, negative 4, 4, etc. on coordinate 2. All right, so that's what the absolute value function can basically be defined as. And so as you see, it's in V-shaped graph. Now this V-shaped graph is what we also call symmetric, right? You notice that the y-axis in this case is what we call a line of symmetry. And every point on here is the same distance away, right? This is 1, 2, 3 units away. This is 1, 2, 3 units away. Even if you chose these two, 1 unit away, 1 unit away. And so we could use that trick there to help us to graph since they are symmetric in the y-axis. Okay, so this can also be found in the book, page 122. All right, so let's move on to actually how we do this. Now, if we were going to take the graph of the function, the absolute value function, it's our main one that's in red. Now what you see in blue is what happens when we play with the different values. The standard form of the absolute value function is what we see here highlighted. F of x equals to a times the absolute value of the quantity x subtract h plus k. Now what we're going to do is just use these little values here to just kind of play with it. In our parent function, it will look like this. This is just a general form when a is equal to 1, when our h is equal to 0, and our k is equal to 0. We will get something that looks like that. Now, if you wonder what I'm talking about, these values here, what you see, I just highlighted, this one here, that represents our a in this function. This one represents the b in this function, or rather the h, that's what it should say. And this one represents the k in the function. Okay, so what you see is that the red line represents the one where all of our values are a equals to 1, h is 0, and k is 0. And so you can see that here if I play around with this a bit. All right, so if you look at this function, you see the value of a that's in front of the quantity x minus h plus the k. And so you see what happens. Now this graph represents the blue graph. So as I move the values of a, notice what happens. As a gets less than 1 and close to 0, it gets wider to the point where it becomes totally flat. And as I increase the values of a, then it becomes narrower and more narrow. And remember, the red one represents the original function in its parent form where a is equal to 0. And so, or a is equal to 1, sorry. So if I drag this to a equals to 1, what you see is that the blue line will come closer and closer to the red line. And I'll just have to get as close as possible. There we go. Now, if I was to move the b value, which actually represents h in this case, if I was to move the h, you see what happens to the function, the absolute value function. Notice it shifts. Now, notice it's x minus h. And so, if I shift it to the right, my values are getting bigger, x minus 3, x minus 4. And if I want to go to the left and shift it to a negative value, then it becomes positive values. So my h value controls the shifting of the graph. And then the last value, the k, if I could get this one working, that controls the vertical shift. And if I go to the negatives, it goes down. All right, so that's how my A, H, and K work. The A controls the width, the B controls the horizontal shifts, and the K, and remember that B really should say H, and that K represents the vertical shifts. We can summarize this with this following table as found in the textbook, that the graph of y equals to the quantity x minus h times a plus k has the following characteristics. The h and the k represent the vertex, and h represents the symmetric line. As we just saw, if a is greater than 0, it opens up, but if we make that a value less than 0, it actually will open downwards. The graph is wider as the value of a uh, is in between 0 and 1, as we saw that, and then the graph gets narrower as we increase the absolute value of a greater than 1. Alright, so let's see if we can match some of these. And I'll show you a little trick here. We're not going to use the textbook version, we're just going to use a trick that makes it a little bit quicker. Alright, so here we have 3 times the quantity of x. Okay, so here we have 3 times the absolute value of x, and we're going to match it here. Now remember, the bigger the value, what happened to the graph? And so here, if we do the same thing here, you'll notice that we have a 3, a negative 3, and a third. Remember, if it was between 0 and 1, that number in front of the a, if it was between 0 and 1, actually got wider. So we know that a is going to be 14 simply because it's wider, but also because it's a positive value and it's opening upwards, meaning that it could catch rain basically. It's like it's smiling. So you could think of it as a very sharp smile means it opens up, and a frown would mean it opens down. Right, so A and 14 are the same. Now what else you can notice is the little trick here. Rise over run doesn't technically work. It works for the first point. So if I use the concept of rise over run just for the first point only, you have to remember that, then I can actually figure it out as well. My rise would be up 1 unit and my run 1, 2, 3. And I could determine it that way as well. And that's the way that I'm going to use. There is another way, it takes longer, but we're going to use this little shortcut. It works all the time. Alright, so now let's move on to number 13. What would number 13 be? And we're going to change that color there. If I use number 13, notice that's a negative 3. Negative means it's frowning, right? And so you could see that already, that this 13 and C go together. And once again, you can use that rise over run concept for the first point, starting from the vertex. That means that I'm going to go down 3, 1, 2, 3, and to the right 1. And that's what you see with the symmetric point. And so we have our C. And then the last one, we're going to make that purple. Number 12 is obviously B. But once again, positive 3. 3 is higher than 1, so it's more narrow. And then also we can use the concept of 3 over 1 to get the first point, which is up 3 units, 1, 2, 3, and over 1, using the symmetric point. Alright, and so that's how we can determine the effect of A. Right, the effect of H and K, what you notice, like I said, with the minus 2, it's actually a positive movement. And minus 2 means you're going to the right. Right, it's just the opposite. And so you're looking for a graph that has shifted 2 units to the right, which will be this one. And so you're looking from the vertex, has shifted 1, 2 units. And so number 15 matches with C. Alright, we could do the same thing for number 16. This is what we call a vertical shift. If you remember the K on that diagram, this is a vertical shift and it's going down 2 units. This is where the sign stays the same. So this one is a vertical shift down. And so 1, 1, 2 would mean that A is 16. And then the last one, number 17, you have y equals to the absolute value of x plus 2. Because it's a positive 2, we do the opposite when we're inside the quantity. So we're going the opposite direction 2 units. and it would actually be this one. It might be a little bit confusing at first, but it all goes back to the original format, that is x minus h plus k. And when you rewrite it, it's positive h plus k, so or comma k, right? So you flip it. So that's the value of the vertex. So the vertex here would have been 0, comma 0, 0, comma 0, 0, comma 0. That's the vertex. All right, so now let's use all of that knowledge to graph an absolute value function. So first of all, you want to know what your a is. So if your a is 2, your h, which is your x value of your vertex, remember it switches the sign to negative 6, and then our k is negative 10. So the vertex is negative 6, negative 10. All right, so we can use the shortcut method. You see in your textbook the long way to do it. I'm going to show it to you using the shortcut. All right, so negative 610 is the vertex. So we go on the x-axis, negative 6 units. And that's going to take us here, about there. And then negative 10 is here, so we see where they meet. That's our vertex. The a value is greater than 0, so we know it opens up. The long way, as you'll see in your book, is that you just choose a point. You could choose a point on the right side of the vertex, like here, or a point on the left side. It doesn't really matter which one because you can use the concept of symmetry to find it. All right, so what we can do here is if we is to substitute a value in, let's say negative 3, negative 1, all right, so let's just go ahead and use our concept of rise over 1, so 2 over 1. We're going to go up 2 units. So from negative 10, that's negative 9, negative 8, and over 1 to the negative 5. We see we get a point there. And then we also use the symmetry, and we have a point there. If we want to know where it touches the y-axis, we can always set our x equal to 0 and solve by saying 2 times 0 plus 6 minus 10, and y is equal to 2 times the quantity 6, subtract 10, so that's going to be y equals to 12 minus 10, so the y-intercept would be 2, 0, 2. And so it's always good to have your y-intercept in there. You see that your line of symmetry is basically going through here, and that's 1, 2, 3 units over, so 1, 2, 3 units reflects. And then you can just simply draw a nice V-shaped graph through those points. And there you have your absolute value function. We can also use the concept of transformation. Remember, this 2 units, this is the original y equals absolute value of x. So we could use the shift to help us. Remember, this means to go 6 units to the left. So if we move this over 6 units, we know it would be here, the vertex. Then this means down 10. So we're going to shift that down to 10. So we know our new vertex will shift over to here. Then we just need to draw out everything else because it's going to now have a value of 2 is going to be more narrow, and we could just use that same idea of going up 2 units and over 1. And so we could use the vertical shifts and the horizontal shifts to help us. We already worked out that the y-intercept would be at 2 and reflect over from there 3 units, and we can draw it similarly and have our V-shaped graph. And you can see the transformation there between the original y equals the absolute value of x and our equation there. Right? If you have to write the equation, we can look at it by determining what the vertex is. The vertex is 0, 4. So that means if I was to write this out in absolute value form, x minus h plus k, I can replace it. I have a times x minus 0 plus my k is 4. All right, I can use my understanding of the a value, and so you see that's 1 unit down, 2 units down, 2 over 1. So that becomes y equals to 2 over 1, or just 2, absolute value of x plus 4. And done. Right? I've just named what that absolute value function is.